is partner with various organizations. And there's no better organization to partner with than the Frost Science Museum. We just opened a new store downtown at the Arsht, and I was very, very fortunate to have a tour of the new museum to be. And we are in for such a spectacular treat that they are bringing their own brand of creativity and insight into the downtown Miami area. And I just want to thank everyone involved with the Frost for making it possible, and also for making tonight possible. To introduce our guest, it's my honor to welcome someone who's become a friend, someone who's very responsible for the museum, and his name is Dr. Eldridge Biff Birmingham, and he's the Chief Science Officer at the museum. He oversees all science content and scientific research, ensuring the accuracy of science in all aspects of the museum's programs, exhibits, and publications. Biff arrived in Miami after more than 2 decades with the Smithsonian Institution, where he served in several scientific research and executive roles. He most recently led the Smithsonian Tropical Research Institute in Panama, which is one of the world's leading centers for investigating biological diversity. He earned a bachelor's degree from Cornell University and a PhD in genetics from the University of Georgia. And I can tell you on a personal note, he gives the most remarkable tours if you ever get a chance to take a tour of that museum. Please welcome Biff Birmingham.
Always have to lower the microphone. Well, it's really wonderful to see you all here tonight. This is an incredible crowd. I think it speaks worlds about our author, who's behind me here, Dr. Lisa Randall. Dr. Lisa Randall. What I'd like to do tonight is just give you a little bit of an overview. I mean, let me tell you why Lisa's here, because it's really, I think, my tremendous good fortune and those of the rest of the museum to have her here. Lisa's written a new book that you all know about. It's the title right here. It's Dark Matter and the Dinosaurs, which I read that title, and one of our exhibit leaders is Jorge Perez Gallego, who's right there. He and Sean Duran on our staff put this together, and I read the title of Lisa's new book, and I'm like, this is incredible, because these guys built this exhibit in the new museum called Feathers to Stars, and it's really a story about the development of birds, the evolution of birds through dinosaurs, the advent of human flight, and then the search in the cosmos for dark matter and things like that. So when I saw the book and realized we were doing this, I called Lisa and asked if she would consider coming down to Miami and giving a talk. And she said, I'd love to, which was wonderful of you. Thank you so much. At the same time, somebody I've known a couple that I've known for a long time, Marvin and Nisa Leibowitz here, brought Mitch to the museum, the story he just told, and we walked through the museum together. And these guys have been great supporters of both us and Books and Books and streaming talks like this. And getting, as you can see, Lisa's packed it in here. There are lots of other people who want to hear the talk. And Isa and Mitch have been responsible for live streaming a lot of these types of events elsewhere. And so they really brought us together. And thank you so much. And then the third, and Lisa's really tired, so I'm not going to go on forever and ever, but I do have to point out that our very first Science Up Close was a little bit more than a year ago. It was also on particle physics. And Pete Markowitz, who's on the faculty at FIU, gave that along with Xavier Cortada, who's an artist and has been working on the Large Hadron Collider. And they just had some great news. So when you're all mugging Lisa afterwards, mug these two as well, because they have some pretty exciting news.
By mugging, he doesn't mean farming.
Be ginger, be ginger. Yeah, she's from Queens, so she can take it. You know, and you know, she has the most incredible biography. And again, because she's tired, I'm not going to go through all of it. But there's two things that I loved about her biography. One, in 1980, she won the Westinghouse Science Talent Search. And I'm guessing a lot of people that introduce her don't actually point to that so much. And the other, and this is particularly for Isa and Marvin, she's also written a libretta. And these are two opera fans here. So I thought you would get a particular kick out of the fact. So we have a particle physicist who's really pushing the frontiers of dark matter. Harvard faculty, for any of you who are academics in the room, she did both her AB and her PhD at Harvard. For any of you who are academics, once you do that, the chances of getting back to Harvard on the faculty are about 0 to none. So they threw her out for a while, and she went on to Princeton, where she became a tenured faculty member at Princeton, and then came back to Harvard, where she is now. So it's really a delight to have her. But I want to give you, if this works, I want to give you just a quick background. So this is the museum. Well, I'm going to talk to you very quickly about the planetarium, the Frost Planetarium right here, and the Exploration Center here, which is where Feathers to Stars is, because that's why Lisa's here. Whoops. All right, so as I've already mentioned, there's a gallery, and it takes you on this evolutionary journey through dinosaurs to birds. And one of the things that Lisa will talk about is what happened to the dinosaurs. And when you think about it, dinosaurs roamed the earth for a couple 100 million years, and then they disappeared. And we've just been talking about the asteroid ever since, and nobody's ever really thought beyond that. And Lisa has. So I think it's really remarkable to think about this exhibit in that context. And this just shows you, we'll have, a lot of people don't know that Tyrannosaurus rex is on that lineage to birds. This is Tyrannosaurus. This is a feathered dinosaur, almost the same size as Tyrannosaurus rex. And you'll see that there. And what I love about this story, because I'm an evolutionary biologist, is that when I was studying at Cornell, I thought I knew pretty much what was going on at that transition between dinosaurs and birds. Now it's a much fuzzier relationship. And I love the fact that Tyrannosaurus is going to be surrounded by things. It'll sort of open this question, are they birds? Are they dinosaurs? Where is that transition point? Will we ever really know for sure? But then it goes from there, and birds, all the way, as I mentioned, to the exploration of space and the cosmos, which is obviously Lisa's principal area of interest and what she'll be talking about tonight. But you start to get a sense of how this program is going to come to life here in Miami at the Frost Science Museum. This is the Frost Planetarium, and of course it's another place where we can develop that narrative about our search, our understanding of dark matter, dark energy, the cosmos in general. And it should be a remarkable resource for the city of Miami, for South Florida, and for the regions. And many of you have heard me talk before. One of the things I love about Miami is our connectedness to the Caribbean and the rest of Latin America. And I think this planetarium is going to be a great draw. And as you see, we can actually project images on the outside. And this is what it looks like on the inside. So it's 8K resolution, full dome. So you'll really feel like you're deep in the cosmos. Or if we move you from the cosmos, we'll take you into the human body occasionally, or deep undersea. But we'll stick for the cosmos for tonight. So it should be an absolutely fantastic experience because you'll feel like you're fully surrounded by that full dome and the 8K resolution. And that just shows you where the museum is now in its construction. It's pretty much fully complete on the outside. We've got a ways to go on the inside. All the exhibits still need to be put there. But I think you'll recognize that it's really next to the Perez Art Museum there. It's just a wonderful, wonderful addition to the landscape and culturescape of Miami. To you, Dr. Randall.
Okay. Good evening. So the first thing I want to clarify is we actually are deep in the cosmos. so we should all feel that way. It's really great to be in Miami. I've actually been really impressed. Miami has kind of a funny reputation when you're not here. So it's really great to see all this interest that there, I mean, seriously, in science, in books, in learning, and it is very exciting that there is so much interest here. And I have to say, I mean, I've mostly talked in kind of big lecture halls, and there's only a few bookstores that I've done, and I've been told that this is just a marvelous bookstore, and I was really excited about coming here. So I want to just congratulate everyone. So I'm going to move on and tell you a bit about my book, and I'm actually going to stand here so I can actually see the slides. Usually I have a computer in front of me. So that's my title. Okay, so I just want to first start because, I think people get a little obsessed by the title. I mean, it's true, it's a fun title. And it is the subject of my research. But really, what I wanted to do, and in some sense it's what the Science Museum is doing as well, is use this as a way of sort of framing the sort of broad history we have of the universe and to getting us here to today. And I wrote this book, because I was sort of thinking along two different lines. One is, actually, before I continue, there are 3 seats that I can see that are empty. So there's lots of people standing. So why don't all those seats get occupied? Okay. And there are more over there? What's it?
That's actually the best view of the screen over here.
Oh, I see. Okay. That's true. Okay. It's up to you. Anyone who prefers to sit and not see. Okay, and I should hold it closer to me. Okay. Just if ever you don't hear me, just raise your hands, and then I'll know, because I probably will forget. And what just happened? Well, there's nothing to see, so people can sit here. Thank you. Okay. All right. Anyway, I can tell you why I wrote the book without the slide. So I've written books about particle physics. That's what I generally do. I do particle physics and also cosmology. Thank you. And cosmology. It's a real challenge to explain these, seemingly abstract ideas. I mean, they're real things, but they're very removed from what we generally see. So one of the things that excited me about the research I was doing now, and was that it does relate to scales that are just more readily visible to us. And so I really like the idea of having a single book that connected all the way down from elementary particles, but dark matter and cosmology, through the galaxy, through the solar system, through life on Earth. I mean, I just think it was important to make that, so that you can see that this is not just something that's out there and it has no relevance, that it's really all connected. And this sort of larger story gave a framework in which I could do that. And the other reason, and actually it's very interesting to be giving this talk in Miami, because I think, we are changing the face of the planet pretty rapidly today. Despite, your governor and people like that, it turns out that things are changing pretty fast. And so it just seemed important to sort of, it's not a book about any of this, but it is a book about how we got here in some sense, sort of the larger history. And so to appreciate a little bit the scales involved, the sort of billions of years of history of the cosmos, the sort of millions of years of history of life, the thousands of years of complex life in us, and to really think about the rapid changes we're making over the periods of hundreds or tens of years. I'm going to try putting this back here and see how that works. It's too weird. So I wanted to sort of contextualize that. So there's sort of a subtle story that lies underneath what I'm talking about. And I say all this because I'm going to spend most of this talk telling you about the story of the research that sort of frames this work. But for me, the book wasn't just about this research. It's really about all the other things that lead into the background that go into it. So before I start telling you about my research, of course, I have to tell you about dark matter. Let me get rid of this. About dark matter, what it is. And it's funny because, when I talk about my things, this is sort of a general reaction of people who feel like it's okay not to understand. It's like, oh, this is all over my head. But dark matter is actually not that complicated a concept. It's really just matter That is to say, it interacts with gravity like matter, it clumps into galaxies, it clumps into gravitationally bound structures like galaxies and galaxy clusters. But it doesn't interact with light, as far as we know. So it interacts with gravity, but not with light. What does that mean? It means it's not made up of the stuff that ordinary matter is made up of. It's not made up of charged particles. It's not made up of atoms. It just is. It's some other substance. We don't know what it is, but it's some other substance. And it's all around us. There's probably billions of dark matter particles passing through us every second, but we don't experience them because they're not interacting with light. They're interacting with gravity, but not with light. So they're interacting very feebly with us. So why do we know it exists? And I'll tell you a little bit more about that. We know it exists because when you have large amounts of dark matter, you can detect its gravitational influence. And indeed, there is a lot of dark matter. There's 5 times the energy in dark matter as there is in ordinary matter. So it's an enormous fraction of the energy of the universe. There's much more of it than there is the matter that we know about. Yet we're relatively unaware of it because it doesn't interact with light. And all our senses rely on the fact that things are made of atoms and interact via light. So we tend to neglect it, but really, as I'm going to argue, it was kind of critical to our universe. It actually gave shape to the universe. Without dark matter, we wouldn't be here in this room today. It really was necessary to give structure to the universe. And it's funny because, people think, like, how can there be all this matter that's not us? People are really disturbed by the existence of dark matter. But I have to say, for me, it's amazing that ordinary matter is as large a fraction of the universe as it is. I mean, we know that we're just some random stuff that's, in some random planet. I don't see why there shouldn't be other types of matter other than the ones that we're familiar with. I mean, why should it all be like us? So this is actually what's sometimes known as the cosmic pie. It just tells you the fraction of energy carried by each of the components that dominate the energy of our universe. And you see that ordinary matter is about 5%. It's a small slice of the pie, but it's a reasonable chunk. Like if I was eating pie, I wouldn't be that unhappy if I had that slice of pie. And that's an important fact. I mean, I'm saying it as a joke, but in principle, right, the amount of dark matter could have been 100 trillion times bigger than the amount of ordinary matter. The fact that the amount of dark matter and ordinary matter is so comparable, I mean, is a really interesting fact. And maybe as scientists, it's actually a clue to what dark matter is, because it is really interesting that all of these slices can be seen. Now, most of that pie is neither dark matter nor ordinary matter. It's actually something called dark energy. I'm not going to say a whole lot more about dark energy, but let me just tell you what it is and why it's there. So dark energy, it's not carried by matter. It's just energy spread throughout the universe, not carried by matter. So why do we know it's there? Because it actually drives the acceleration of the expansion of the universe. As we'll talk about on the next slide, we know the universe is expanding. Ordinary matter, you would think, would slow it down. It's gravitational pull. But dark energy, which is badly named, it's really kind of negative pressure, drives the acceleration of the expansion of the universe. And it's just spread uniformly throughout the universe. It's been constant over time. It's spread uniformly. Whereas ordinary matter is clumped into all the kinds of structures we see that eventually leads to us in this room. Dark energy is just spread throughout. So it's not matter. It's something totally different. Now you might say, why am I concentrating on dark matter when this is 70% of the energy? Well, the fact is we are making some progress in understanding, but dark matter is something that we are really primed to make a lot of progress on. There's a lot of ideas for what dark matter can be. When I say what it can be, I mean, people get confused because it's not that we don't know that dark matter exists. As I'll explain, we really do know dark matter is there. We see its gravitational influence. What we don't know is what it's made of at a fundamental level. Is it made of elementary particles? If so, what are those particles? What are their mass? What are their masses? Do they carry any charges at all? Is it just one type of particle or is it many? So we'd like to know what dark matter is, but there are many theoretical ideas. I do theory, so we have models for what it can be. So there's many theoretical ideas, and there's also a lot of observations and experiments going on that might help to test these ideas. dark energy is definitely there and people are studying in more detail, but I think that we're really primed to make progress in understanding dark matter in the next few years. So how do we know what those slices of the pie are? Well, we know them in several different ways, but one is by measuring something called the cosmic microwave background radiation. That is the radiation left over from the time of the Big Bang. So the universe initially exploded in sort of this hot Big Bang that you hear about, where there's hot radiation that then cools down. But then we can measure that radiation in detail. So what this slide is showing is sort of a sketch of what the evolution of the universe is. So actually, despite the name Big Bang, no one knows what banged. So the Big Bang theory is actually a theory that tells us about the later stages of the universe. And by later, I mean only a fraction of a second after it started. But we don't know what happened in the very beginning. Anyone who tells you they know what happened in the very beginning is not telling you the truth. They're ideas, people speculate. See, that's how upset people get. So people can speculate about it, but we don't know what happened at the very beginning. What we do know is that pretty early on, maybe 10 to the minus 38 seconds on, so very early on, there was an explosive expansion. So the Big Bang theory, things are exploding pretty smoothly. Early on, there was an exponential expansion, a very rapid expansion of the universe. And really, in some sense, that you can almost consider the Big Bang because that's what set the conditions for the matter that we see today. That all came at the end of inflation, over which a smooth expansion takes over. And there's lots of ways that these theories are tested. That is to say, observations that support this. I mean, one is just the fact that the universe is indeed expanding. If you measure galaxies, you can see that they're moving away from each other. That was Hubble's observation of what's known as the redshift of galaxies. We can also know things about the amount of heavy elements in the universe. That's why it talks about nuclear fusion. But the other measurement that was really critical to establishing the Big Bang theory was the fact that there is this cosmic microwave background left over on the sky from the time of the Big Bang. And actually, I'm not going to go into details, but by measuring details of this radiation, we actually verify that there was this explosive stage of expansion. Furthermore, it also supports it also tells us what the fraction is in ordinary matter, in dark matter, and in dark energy. And so we know about this from the radiation. That's what established those sizes of the pie. But there are other ways we know about dark matter too. But before I say that, I just want to again emphasize, because this is confusing to people, none of this, anything I've told you so far, is speculation. We really know that dark matter exists. And we know that dark matter exists in part from that radiation, but also the way that we first knew about the existence of dark matter was because dark matter, if there's enough of it, exerts enough gravitational influence that could affect the motion of other objects. So even though it itself is not shining, it's not visible, it affects the motion of visible objects. So originally, actually, it was first just identified in the 1930s in the Coma cluster. A cluster of galaxies is a gravitationally bound group of galaxies. And it was noticed that stuff in that cluster was moving more quickly than could be supported by the visible matter. That is to say, the matter that was there was not enough to account for how that stuff was moving so quickly. So Fritz Zwicky actually suggested that there was this dark matter. We didn't know what it was. But Fritz Zwicky was kind of an interesting character, and no one actually believed it at the time. So it really wasn't until the 1970s that people started to take this notion of dark matter seriously, in part because of the work of Vera Rubin and Ken Ford, who actually looked at the Milky Way and measured the speed of stars, the motion of stars in our Milky Way. And they found that here, too, stars were moving more quickly than could be accounted for by just ordinary matter. In fact, if there was just ordinary matter, the gravitational pull wouldn't suffice, and the stuff would just fly out. So it's going around in a circle. You need some gravity to pull it in. There wasn't enough gravity from just ordinary matter, and if you just had ordinary matter, the stuff would fly away, which was strong indication that there at least some matter that was not visible existed, and that is indeed the dark matter. But there's a couple of other ways I'm just going to mention that we actually know about dark matter, and they're kind of cool because they're sort of almost like seeing dark matter, but they're not quite. So what are those? One is known as gravitational lensing. So this is kind of a complicated slide. Let me just walk you through it. It's not that complicated, come on. So on the left we have the observer who's on Earth, right? And then on the right, sorry, am I standing right in front of you? Yes, I am. Okay. I'll go in the place where you can't see. You can't see? Okay. Okay. I'll try to tell you what you're not looking at. Okay. Yeah, that's true. That would be very useful. Do you have a mechanism for doing that here?
That's not theory. That's
Okay. Yeah, you need the multimedia space that you'll have in the Frost Museum. Then we can do the talk there, and everyone can see it at all angles. Okay, so we have on the left we have the Earth, on the right we have a star, or it says object, but it's a star. So that star emits light. Now, so when that light passes by dark matter, so we don't see. Oh, good. Visual aids, fantastic. So we don't see the dark matter, but the dark matter bends the light from the star. So it itself is not emitting light, but affects the light emitted by another object. Now, the interesting thing is that the light bends differently depending on how it goes around the object. So when we actually look back, we project back into straight lines. So we think that we see multiple images of the same object. It looks spread out. Instead of seeing just one object, it looks like there's many images, or a spread out image. And this is known as gravitational lensing. And this is actually a way that you can map not just dark matter, but also dark energy by looking at lensing effects. Now, something else that's really interesting is that there are clusters of a galaxy like the bullet cluster illustrated here. Now, the bullet cluster is, again, a cluster of galaxies is a gravitationally balanced set of galaxies. The bullet cluster is actually formed from the merging of clusters. Now, clusters of galaxies have gas in them, and they also have dark matter in them. Now, what's going to happen when those clusters of galaxies merge is that the gas will actually get stuck in the middle, whereas the dark matter will just pass through. And that's actually precisely what's observed. You see that in the middle, and you can see the gas through X-rays, because it does emit light. But then you see through gravitational lensing that there's dark matter on the outside. And the reason I like this is because, people are skeptical, sometimes rightfully so, and they're like, maybe it's just that you're modifying the laws of gravity. It's not really dark matter. So first of all, I just want people to understand that modifying the laws of gravity is far more radical than assuming there's dark matter. I mean, dark matter, as I've said, there's no reason for it not to exist. It's just a different type of matter. Modifying the laws of gravity would be a pretty major thing. It would tell you that your fundamental laws of physics are different. But what I really like about this is it shows why it's really hard to accommodate what we see with just modifying the laws of gravity. I mean, this looks exactly like what you'd expect if there's dark matter. That is to say, the visible matter, we know it interacts with itself, it gets stuck in the middle. Whereas the dark matter would just pass through because it's not interacting a lot with itself or with ordinary matter. So this is exactly what you would expect if dark matter exists. Where is the dark matter? Well, it's all around us, but it's really surrounding us in an enormous, approximately spherical halo. So what the galaxy actually looks like is this halo of dark matter with the Milky Way plane inside. So the Milky Way plane, it's a little hazy in Miami to see it, but other places that are drier, you can see this bright band of stars and gas that is the Milky Way. That's ordinary matter. You might ask, why is dark matter in a spherical halo, whereas ordinary matter is in this plane? And the reason is precisely because ordinary matter interacts with radiation. And because of that, ordinary matter can cool down because it can emit photons, which carry light. So it can emit photons, get rid of some energy, it can dissipate energy, and then collapse into a disk. And this is important because it's important for the dark matter story I'm going to tell you. But this is actually the structure of our Milky Way, of our galaxy, that is. So the Milky Way collapses because ordinary matter emits light. It can collapse into a thin region, the Milky Way plane, and it's surrounded by an approximately spherical halo of dark matter. So I kind of like to think of dark, I have a lot of social analogies in my book, which you may or may not appreciate. But I like to think of dark matter, it really does work very well, because dark matter was kind of essential to our universe. You might say, why do we care about dark matter? Well, actually, galaxies would not even have formed in the lifetime of the universe had there not been dark matter. Because if you think about it, radiation doesn't collapse. It's only matter that collapses to form structure. And because of the existence of dark matter, there's 6 times the amount of matter that there would otherwise be. Now, the thing is, in the early universe, it's dominated by radiation. But radiation dilutes more quickly than ordinary matter. It dilutes more quickly because, in addition to just the expansion, it also redshifts. So ordinary matter becomes a bigger and bigger fraction of the energy of the universe as the universe expands. But had there been only ordinary matter, it wouldn't have had enough time to collapse into structure, because structure can only form when matter dominates. And furthermore, if there had been only ordinary matter, smaller structures, such as galaxies, wouldn't have formed because radiation would have washed out any structure that there would have been. So dark matter was essential for 2 reasons in order to form galaxies. And without galaxies, nothing else of interest to you would have formed. So dark matter was really essential to everything we see in the universe. And like I say, it's kind of like the unsung hero. Like we often focus on sort of the leaders and the bright stars, but we neglect all these underlings who are building things and making everything work. And so dark matter kind of played that role. It sort of was there to establish all the scaffolding. In fact, ordinary matter could only collapse into galaxies because dark matter had done so, and then kind of it hitchhikes along and comes along for the ride. So really, dark matter was essential to everything we see. But, as I said, we know that it's there, we know that it was important, but we don't know at a fundamental level what it is. Again, we don't know as a particle what it is, what it's made of, what's its mass, what are its charges. Is it just one type of particle? Those are the kinds of questions that we want to answer. And like I said, I think we're poised to make a lot of progress, both because of the kind of theoretical work that my collaborators and I are doing, and many other people, and because of observational and experimental work. And I don't have time to tell you about all of it now, but I do talk about that in the book, just all the different ways that we're now looking for dark matter. And one of the reasons, I should say, that I think the kind of, even though the work I'm going to tell you about now, and a lot of the stuff I do is speculative. We're making hypotheses for what dark matter can be. One of the reasons I think it's really important is because these observations are so difficult, because basically experiments are so difficult. Unless you have some idea what you're looking for, you're not going to find it. If you're looking for a needle in a haystack, it helps to have some guidance where you're looking, or else you'll probably miss it. And so what models do, they provide targets to look for it, and they also tell you different ways that you might even hope to find it. So the basic insight we had, which is going to sound pretty obvious, well, maybe it will, maybe it won't, but it is kind of obvious, is like, why should ordinary matter be that special? I mean, we know that ordinary matter is made up of many different types of particles. Those of you who know particle physics know that it's made up of quarks, it's made up of particles called leptons, electrons, muons. There's many different types of particles in what's known as the standard model of particle physics. Yet, we, and by we I mean the entire physics community, assumes that dark matter is just one type of particle. So we made that what we think is not very radical assumption of saying maybe dark matter has an extra component. Maybe even though most of dark matter is this non-interacting thing that forms a spherical halo, we said maybe some small fraction, even 5% of the dark matter is something that has some interesting interaction. And in particular, we said, just the same way that dark matter doesn't interact with the light from ordinary matter, maybe dark matter interacts by a light that ordinary matter doesn't experience. That is to say, it experiences dark light, a light that only dark matter experiences. So if that's true, dark matter would interact with itself. It would more strongly than just gravitationally, but it's not interacting with ordinary matter. Now, there's a couple of reasons you might have not wanted to think about this. I mean, one is, people like to think that things are as simple as possible, Occam's razor, but it's not actually clear which is a simpler assumption. After all, if we were dark matter particles looking at our sector, if we were dark matter people looking at our sector, and we said maybe it's just one type of particle, we would have been badly wrong. So maybe it's more reasonable to just, or simpler, to think that the dark sector is somewhat like our sector. And the other reason you might have thought this isn't worth doing is we haven't even identified what most of the dark matter is. Why would I care about a small fraction? But if you think about that for a moment, you'd be really wrong, because if you had that logic, you would say, why do I care about ordinary matter? After all, it's only 15% of the matter of the universe. But we care about it a lot, for one thing, because we're made up of it, but for another reason, because of its interactions. And its interactions, as I said, give rise to the Milky Way disk, but it also gives rise to all the other structure that we see. So something with other interactions is, in principle, easier to observe, and that's why we want to think about it. So it doesn't mean that it's necessarily true, but it does mean that there's a chance to test it, and maybe even test it before we know about the bulk of the dark matter. And the other reason I personally really like this research and also liked writing this book is that it really helps to have different fields of science coming together. I mean, it might not sound so distant, but we really are particle physicists and cosmologists. We're not astronomers. Now, when astronomers look at things, on the whole, they're trying to fit the things that we already know. We come from a particle physics background where, as I said, we have models, and we try to say, how do you test for whether or not these models are right? So it's a different perspective, but we benefited a lot from the many methods in astronomy, and we're hoping they benefit from our thinking about particle physics. And as I'll tell you a little bit, in the dinosaur story, many other fields of science came together too. So this was a way to sort of see that, when we're talking about the universe, we really are talking across disciplinary boundaries, and that was very exciting for us as well. So the picture that we ended up with is that maybe this little fraction of dark matter is like ordinary matter in the sense that it radiates. And just like ordinary matter radiates and forms a disk, maybe this extra fraction of dark matter could also radiate and cool down and collapse into its own disk, a dark matter disk. And the thing that was particularly interesting that none of us had anticipated is that if a dark matter particle is heavier than a proton, as we would expect it to be, this disk will be even narrower than the disk of the Milky Way. And that will be very interesting for the reasons I will tell you about. It's also what makes it potentially observable. So there are observational consequences because dark matter in the Milky Way disk would actually affect the motion of stars, because stars go up and down around the plane of the Milky Way, and they respond to the gravitational potential. And one of the really nice things for us when we were doing our research, and as particle physicists, I mean, most people who know about particles know that these experiments take forever to do. They're wonderful, they're ambitious, but they take a long time. When we were doing this research a few years ago, that very fall, a satellite was set to launch that was going to do exactly the measurement we wanted, which is to say it's measuring 1 billion stars in the Milky Way. It's measuring its position and velocities. And with that information, we will know about the shape of the galaxy. We will know the gravitational potential. We'll actually be able to tell if this dark disk exists, and if it does, what are its properties. So whatever you think of this, you could say it's nonsense, you could say it's speculation, and the point is it's science, because this is what you do. You have ideas for what things can be, and then you go ahead and test whether or not it's right by doing observations. And the great thing about having a model is these observations were going on anyway, but it was measuring things that they didn't even know they were going to measure. So by having this target, we really learn more about the shape of the galaxy. But, as the title of my book indicates, there are other consequences too. So I'm going to switch gears now, and actually the first third of the book is about cosmology, but the second third is actually about the solar system. And in particular, it concentrates on cool stuff like asteroids and comets that can hit the Earth. It also tells about life on Earth and extinctions on Earth. And in particular, so it talks about the 5 major mass extinctions, but it really has an entire chapter on the extinction of the dinosaurs. Because, you know, when I started this research, and I will tell you why this might be connected. When I started this research, I mean, I'd heard about the impact hypothesis for the extinction of the dinosaurs, but it's not like this has actually been around for that long. You know, it's interesting. You might think of it that way, but it's really only in the 1980s that people really started to take it seriously. What I hadn't appreciated is how strong the evidence is now that an impact happened around the same time. There could be other things contributing. There could be other stuff, but there's a lot of evidence in the form of the rocks, geological evidence. But also, the exciting thing is that we've actually identified, or the researchers back then actually identified, the actual crater corresponding to the impact that happened 66 million years ago. So I'm going to get to that. So let me just take a step back now. So I've told you about cosmology. We're going to take a couple of minutes to just reflect on the solar system so we can understand the story I'm about to tell you. So the solar system, there's the 4 inner rocky planets, which are much smaller. There are the 4 outer gaseous planets, and there are only 4, because as you know, Pluto was demoted. But actually the demotion of Pluto is actually a really exciting thing, because what it really represented was the fact that other objects were discovered in something called the Kuiper Belt. So it was the fact that Pluto wasn't alone, and there were other objects comparable in size, at least 1 or 2 comparable in size, that made them say, you know, there should be a separate category for these things that are in this other belt. So there's the asteroid belt between Mars and Jupiter, and then there's this Kuiper belt, which is close to the source of short period comets, which is actually the scattered disk. So the reason Pluto is no longer a planet is because, you know, it's kind of the grade school logic of, you know, if we let you in, we're going to have to let everybody in. And so they thought it was just simpler just to have its own separate category and not have to worry about it. So we're now left with 8 planets and Pluto in a separate category known as dwarf planets. But so again, we have the asteroids, which are just basically rocks. You know, asteroids are just rocks of various sizes, and they really do range in sizes. And there's more of them the smaller you get to. And the asteroids hit the Earth all the time, or at least the atmosphere. There's, meteors are basically asteroids, or micro. But in the outer region, beyond Neptune, is the Kuiper Belt, which is a source of close to the source of short period comets, which is technically the scattered disk. But much, much farther away is something known as the Oort cloud. Now, the Oort cloud is basically at what you might consider the edge of the solar system. I actually have a whole chapter saying what the edge of the solar system is, because it's actually a confusing thing. But thousands of times farther away than the Earth is from the sun is the source of long period comets, and that's known as the Oort cloud. Now, the thing about the objects in the Oort cloud is it's so far away that the stuff there is only very weakly gravitationally bound to the sun, because it's so far away that the gravitational force is really weak out there. What that means is that if there's anything that gives even a tiny kick, a small kick, it has the potential to knock it out of its orbit. And when it's knocked out of its orbit, it could just leave the solar system altogether, or it could, in principle, be more likely to come towards Earth, because things in the orbit are not going to hit the Earth, but things that get knocked out have the potential to come into the inner solar system and hit the Earth. So, and I just want to point out that lots of stuff does hit the Earth. Again, most of the stuff that hits is pretty small, but larger things do hit. And this is one example. This actually isn't one of the bigger ones, but it's actually about a kilometer wide impact crater in Arizona. It's known as the Meteor Crater. It's also known as the Barringer Crater. And there's an interesting story behind this one. There's actually an interesting story behind almost all of them. But at the time, people didn't really know that this was an impact crater. And it's very inconveniently located actually near a lot of volcanoes. So people thought it was a volcano. But Daniel Barringer, who was both a businessman and a mining engineer, was pretty convinced it was an impact crater. They found some iron meteorites. So he not only was convinced it was an impact crater, but he thought it would be the source of a lot of iron, not understanding that most of the stuff vaporizes when impact craters are formed. So he actually did a lot of work to show that it was in fact an impact crater and did succeed. However, because he thought he was going to find this great mine or great source of iron, he actually lost a lot of money in the process because there's not a lot of iron there. But there's a whole lot of stuff that's pretty big that's hit the Earth. And this is a list. So if you go to the web, you can actually go to something, this is what we did, called the Earth Impact Database, where every impact crater is recorded, both its size and the age, its age, to the extent that they know it. So my collaborator Matthew Reese and I at Harvard were interested in the question of whether big impacts happened periodically. That is to say, we know most stuff hits the Earth randomly. All the small stuff is random. It's coming from asteroids and stuff. But could there be some additional population that contributed to something that happened on a regular basis? Now, the only thing that could be the Oort cloud. So is there something that triggers things getting dislodged from the Oort cloud on a regular basis? Now, we weren't the first people to think about this, but there's sort of marginal evidence, if you look at the crater record, that this is happening periodically. So we looked at craters bigger than 20 kilometers. That's pretty big. Bigger than 20 kilometers means it was formed by a kilometer object that hit the Earth, that are there from the last 250 million years. And the Earth is a pretty active place geologically, and most of it is ocean. So there's actually a lot more stuff that hits than is actually recorded. But the number of craters of this set is about 27. So there's about 27 that are bigger than 20 kilometers. That's kind of a lot, actually. But it's from 250 million years, so it's not really that many. But it is kind of amazing. So it's almost big enough to do a reasonable statistical analysis, but as you can guess, it's always going to be somewhat marginal. So the evidence is a little bit marginal, but there's some evidence that this happens on a regular basis. And the period is about 30 to 35 million years. And that's actually what we found. And we found better evidence having had a model. Now the question is, why would this happen? Well, there's been several suggestions for why this might happen, but here's the one that we looked at. The other ones are basically ruled out. So people suggested there's maybe a star in a big orbit with the sun. It was never found. It's not stable. They thought maybe it's crossing the spiral arms. That could cause it, but we only cross the spiral arms about every 80 million years, and we don't actually do it periodically anyway. But one explanation seems somewhat promising. Now that has to do with the fact that the solar system actually orbits around in the Milky Way every 240 million years. But as it does so, it bobs up and down through the Milky Way. So if something happened when it passed through the plane of the Milky Way, in principle, that could trigger impacts. Now without dark matter, that doesn't happen often enough. It would only happen about every 55 or 60 million years. And also, the Milky Way disk doesn't vary in density enough. But with this dark matter disk, it's possible that it could be about 32 million years, and that every 32 million years it goes through the dark matter disk, and the gravitational force from the dark matter actually dislodges stuff from the Oort cloud. And that was our suggestion. And we actually found that it's statistically preferred to just random. It doesn't mean it's right, but the interesting thing about it is we know roughly what the properties of that disk would have to be in order for this scenario to be true. So although we're not going to be able to necessarily test this hypothesis directly, we can test whether the dark disk of the sort we would need actually exists. And those measurements are going on right now from the Gaia satellite. So finally, this brings us home to the dinosaurs. So the other thing that I was fascinated by when I was writing this book was just the record of life on Earth. And just, of course, life has been around for billions of years. Actually, it's not of course, it's kind of amazing. Almost as soon as life could really start to form, when things stopped getting hit by meteorites, life started to form a few billion years ago. It's kind of amazing, even more than that. But complex life is really around for about 500 million years. Since that time, there have been 5 major mass extinctions. And that's kind of incredible. Major mass extinctions are basically where 1/2 to 2/3 of the species on the planet disappear. So we think of evolution as a smooth, continuous process, but really 5 times that we know of it really just got reset. And there have been minor mass extinctions as well, and also local mass extinctions. And those have a much more cataclysmic impact on life. Life recovers, it turns into something else, but it's pretty major. And actually, when I first started doing this, it was the first time I had learned about the sixth extinction. And at the time I started writing the book, no one else had really written about it or heard about it. And I was like, why doesn't anyone write about this? And then like a few months later, a book came out, because it seemed like a pretty important thing, especially in the context of climate change. But the one extinction that I'm focused on now is the one that happened 66 million years ago. Because that is one that we actually know was associated with an impact. We don't necessarily know in detail how stuff died, but we do know that if there is an impact, basically every disaster scenario except a zombie apocalypse will happen. I mean, really everything happens. There are fires, there are earthquakes, there's gas that goes into the atmosphere, there were tidal waves, there were many different things. And the story of how we put together some of the stuff of how life went extinct, and there could have been excess volcanic activity as well that got triggered by this impact. There were a lot of things that changed the face of the planet in ways that most of life went extinct. Stuff that survived was stuff that could basically bury underground or fly in the air, which is why we still have birds, even though we don't have terrestrial dinosaurs anymore. So that's basically the story. But the reason I'm showing this slide is because it's actually pretty funny. I was actually on the Big Bang Theory because I have friends who write for it. And I was visiting, and they said, you know, why don't you... Well, it's kind of like, it's a lot of fun. It's really interesting. But they basically said, you know, why don't you just like sit in the cafeteria? So my job was to be an extra. So it's pretty funny. So my direction was literally just sit there and be inconspicuous. So I was apparently a really good actor because I was so inconspicuous that even though like I'm right there, like most people who saw it didn't realize I was there. And the reason I show this slide is because I'm very proud of it. No, it's because it just emphasizes the fact that unless you know to look for things, you usually miss them. And so, I mean, and this is pretty obvious. Imagine what's going on at the Large Hadron Collider, where finding the Higgs particle, you're looking for one event out of a billion. And when you're looking for things, it really helps to have models. So even though these models are all speculation, most of them will be wrong. You learn more by knowing what you're finding and what you're not finding if you have a target to look for. So I'm not telling you that the theory I told you is necessarily right, but we will learn more about the shape of the galaxy by asking whether or not this is right. And I think that's really important. So I just want to close with some words about a little bit more about the sort of broader context of the book. And I actually started in the introduction by saying like 4 kind of general lessons that I learned in writing the book. And they are general, but like one is really by studying the universe from its very beginning to where we are today, you really get to appreciate more some of the amazing connections that exist. And you know, we know that dark matter was essential to galaxies forming, but there were other things that I hadn't really thought a lot about, like the fact that nuclear decay is what drives the movement of continental plates, which is what in part drives the carbon cycle, which is essential to life on Earth. I mean, there's all these connections where we're connected to the properties of much more fundamental matter that affects how things are today. And of course, a lot of people know that heavy elements that are essential to life, like carbon, were formed only because supernovas formed them. But something I hadn't appreciated, again, until we were doing this research, was for things to cool to the point that stars could form, you required molecular cooling. It wasn't just enough that it dissipated radiation, but you needed molecular cooling, and that also required heavy elements. So there are all these amazing connections, and I try to point them out throughout the book, of just how the properties of elementary matter connects to what we see today. Oops, sorry, that was a little bit premature. But I also point out some 4 major lessons for me, which are, in some sense, just how amazing it is how it all fits together. I mean, that sounds kind of gee-whizzy, but there really are these very detailed scientific connections that are amazing. And the other thing that I really do find impressive is how much of it we've been able to figure out. I mean, a lot of time, you know, I'm talking about research, I'm talking about all the questions we don't know the answer to. But it is kind of incredible how many things we have figured out. Another thing that really struck me when I was writing it was just how recent so much of this is that we figured this out. I mean, no one even knew the universe was expanding. No one knew about the theory of gravity until about a century ago. I mean, we just celebrated the anniversary of the theory of general relativity, the century. So we didn't even really have a starting point for cosmology until then. And the amount we've discovered, and not just in cosmology, not just in particle physics, but even in understanding geology, and how connected our understanding of geology is to all of the ways our industrial society has developed. I mean, that was really striking as well. The other thing is sort of the many fields of science that enter. I haven't had time to tell the whole dinosaur story, but to figure that out required physicists, chemists, geologists, paleontologists, all working together to figure this out. And I think the other thing that really keeps coming up again and again is the importance of the rate of change. I mean, I mentioned briefly the debate in evolution. You know, Darwin thought everything happened slowly. Cuvier, who was the first to really understand that extinctions happen at all, thought everything happened catastrophically. Well, clearly both play a role, and both play a role in the evolution of the universe. But it really makes you think about it. So a lot of the things that people say are happening today for the first time aren't necessarily happening for the first time, but they're happening very quickly. And the question is how you deal with it. So I think think about the pace of change is very important. I'm just going to show you just a couple of pictures just because they're fun, and then I will conclude. So this is actually, I was very lucky. I'm not a field researcher. I do theory. But I happened to be visiting the University of the Basque Country in Bilbao because I was visiting Spain, and they invited me to give a lecture there. And they know I like the outdoors, so they took me on a walk on the beach. And so one of the physicists I had just met said, my cousin's a geologist, and the KPG extinction boundary is actually very close by. And he didn't even know I was working on it, but the KPG extinction is the Cretaceous-Paleogene extinction where the dinosaurs went extinct. So it is this layer where you see this white rock, which is Cretaceous actually stands for Cretan earth. It's Creta, and that was actually limestone. And that limestone is formed by fossils. And so it's very white rock, separated by a layer of clay that came from the impact. And then above it is grayer rock because most of the stuff went extinct that would have formed that whiter rock. So it's this really amazing layer that you really see this distinction. And it was just right nearby. So the next day we organized an outing to go visit. And this is the guy who heads what's called a geopark in the Sumaya beach. It's an amazing place. And it's not just this that they study there. It's many years of history, millions of years of history because of all the limestone that's there. And if that's not enough reason to visit it, it happens to be like the most beautiful beach you've ever seen. So, I would highly recommend if you're in that area to go visit there. And I have to say, it's just a lovely thing because it's this thing called a geopark. They actually really do scientific research there, but they carefully preserve it. But they also encourage tourism in a very responsible way. It's actually a very impressive thing. I was really amazed. So, as I said, I don't know for sure that the dark disk idea is right, and I don't know that if it's connected to the dinosaurs, but I do know there are all these amazing connections, and this is one of the ways we go about figuring them out. So if you want to learn more about it, this is where you can. So, thank you. So, if you have questions, I can answer a few questions. Yeah.
Why doesn't a piece of dark matter just collide into a piece of dark matter?
If it did, you wouldn't know about it because they're only interacting via gravity. So even if they passed right through each other, they would pass through each other. They're just not interacting very strongly.
Is that small? The dark matter, is that much smaller than or bigger than?
It's not that it's smaller. It's just that it's only interacting gravitationally. So it would, don't forget, most of ordinary matter is empty space. So there just wouldn't be a whole big collision there. So you really need a lot of dark matter. And I kind of joke about it, but you really need a lot of dark matter to actually see its effects. Yep.
Thank you. Our son is a graduate of these fine gentlemen's program at FIU. And by the way, he's now teaching. Anyway, and I have a lot of fun, carrying on discussions with him. He loses me pretty quick. But I have a question, though. Although the percentages of the makeup in terms of the ordinary matter and the dark matter are vastly different. Would that kind of relate to this theory of parallel universe?
No. I mean, there could be parallel universes. I actually talk about in the context of cosmology, the idea that there's multiple universes, but those are really just disconnected. You know, there's some tendency we all have, or I don't, but everyone else does. You know, it's like, this stuff is invisible. Maybe it's all the same thing. So, you know, I worked in extra dimensions, but there are many different reasons things can be invisible. And one is that it's just so far away that light doesn't get to us. So we talk about other universes, that's usually what we're talking about. Yeah.
In all these theories that nobody can check, like supersymmetry, etc., are there
Well,
any?
they try to check.
They try, but they don't find it.
They haven't found it yet.
Are there any theories that would have symmetry or connection to dark matter elements, or are they all?
Yeah, that's actually a great question. And the reason there actually are theories like that, and the reason is precisely the fact that the amount of dark matter is so similar to the amount of ordinary matter, makes it look like there should be some sort of connection. And the mystery about ordinary matter, we know what it is, but why is there matter, so much more matter than antimatter? And antimatter is stuff that has opposite charge and could just annihilate with ordinary matter and just turn into energy. But the fact that we're here talking about it means there's more matter than antimatter.
But you don't need dark matter.
Right, but people suggest that maybe dark matter is like that. And there's also an asymmetry of dark matter over anti-dark matter. And those asymmetries are connected. So that's one way that people try to do it. It's not like supersymmetry, but there's a possibility that it's a similar mechanism, that because we know with matter that it has to be a matter asymmetry over antimatter. So they say maybe dark matter is more similar to ordinary matter than we usually assume.
Quick question. If there's a dark matter disk, does that have to be in the same plane as the ordinary matter disk?
Great question, actually. And it doesn't, but gravity would tend to align them. So in the lifetime of the galaxy, you would expect them to be aligned. Yeah, so we can experimentally test that, but that's actually what we expect. Yeah, Alan.
You said that every 32 million years is a giant collision.
There could be. I'm saying it's more likely to happen every 32 million years.
When are we there?
Well, we actually are on the right side of history. So we passed through about 2 million years ago, so it won't be another 30 million years. So we have a lot of other things to worry about before then. You and Miami have a lot of things to worry about. Yeah.
What happened 32 million years ago?
There actually were big impacts. They just weren't big enough to eliminate all of the life on Earth. What?
Nothing yet you can mention that.
I can. I don't remember the name, but it's on that list I gave you. You can look it up. I'll get to this side of the room in a minute.
So you sort of point to the end in one of your last slides that, you know, how we find knowledge. And the question for me is, it's really weird given dark matter and its gravitational forces that physicists didn't kind of figure it out until 1970. They first saw it in 1933, but how do you explain that? I mean, given
I think it's just, so my explanation is, just imagine like when you can't find your socks. You're like, they're probably here somewhere, I just haven't found them. I think, you had to really do careful measurements, and I think they just didn't have the capacity to do careful. So, I think the more likely theory was maybe some of the stuff is dark, it's just not emitting enough light for us to see it. You have only so much sensitivity. So I think people just thought that they were just missing some stuff, or maybe it's not a new form of matter, maybe it's just stuff like Jupiter's that are not emitting light. So
it kind of seems like there were socks everywhere, and the physicists weren't picking them up.
I think that's true in some sense, but again, lots of people lose their socks. So I don't know.
Not me.
Okay, I promised this side of the room. Was there something on it? Yeah, go ahead.
I've got two questions. One's dumb, the other one's dumber. The dumb one is, one of the main reasons you need dark matter is to explain the gravitational forces that shape our current universe. Is it at all possible that the explanation is simply a lot of black holes, maybe?
So people have considered black holes as a candidate. Yeah, so black holes have been considered as a candidate for dark matter. The thing is, black hole so some black holes, if they're too small, would decay away. Black holes that are too big would actually influence various things. So at this point, there's enough observational constraints that if it even is allowed, it's not even clear it's allowed. It would be a very narrow window. I mean,
Black holes, like you said, small ones.
well, for example, like it would have lensing.
Being made again.
Yeah, it's just that we would see them in other ways, like through lensing, for example. I mean, there's other effects, or it could make things go out of their orbit as they pass through the plane of the galaxy. So there's various constraints. So if they are there, it would be a very narrow window, and so it's probably ruled out at this point.
The dumber question has to do with.
That wasn't a dumb question, by the way.
You touched before on other dimensions. With string theory, it looks like there's somewhere between 11 and 13 dimensions.
Not
that
exactly,
are
but that's okay.
well, that
There's more
I believe
dimensions.
need to exist for string theory if it is in fact going to be valid. And my understanding of these other dimensions sound a lot like the way you've described dark matter. They permeate our universe. They're just sort of like curled up into themselves, and that's why we don't interact with them. Is it possible this dark matter is actually within other dimensions?
So I actually have a whole book about extra dimensions, which is my first book, What Past It Is. And it's not as simple as that. I mean, because it's a question of where the energy is distributed. And so it is possible that dark matter exists in the context of these other dimensions, but you have to keep in mind that dark matter is like clumped into galaxies. You can't have dimensions clumped into galaxies. That doesn't make sense, really. I mean, you could have you would see other effects, in other words, of the fact that it's changing, but it's just a question of the nature of what it is. So you could have dark matter that exists in the context of extra dimensions. It could be associated with phenomena in other dimensions. But the thing is, my attitude is generally, although I talk about very speculative things, is like you want to sort of build up like one speculation at a time. I mean, there's so many reasonable candidates that don't require exotic things like extra dimensions for what dark matter can be, that until we rule those out, we're never going to know whether anything else like that is true. Okay. Okay, just a couple more questions. Yeah. Yep, you.
I just was wondering, how does magnetic energy fit in with the dark matter and dark energy? Because apparently it's supposed to be a big driving force in the universe as well.
Well, I can tell you that when we are working out the constraints on like what's actually in the disk of the galaxy, you have to take into account the magnetic fields. But it's not really magnetic energy, it's just the magnetic fields which affect the distribution of what's there. So, I mean, it's just you have to do everything consistently. So it's just one of the forces that enter. But again, magnetism only interacts, is basically like light, so it's really only acting on ordinary matter, the kind of magnetism we're familiar with. Yeah, in the back.
You talked about how dark matter doesn't really react to standard matter or interact. Does dark energy have an interaction with?
Yeah, okay, so let me just say something about dark matter and dark energy, which is they're both terrible names from the point of view of understanding what they are from the physics. I mean, dark matter isn't dark. Dark things absorb light. So dark matter is really, it's transparent matter. Dark energy is also really badly named because, again, it's not absorbing light. It's actually has to do with negative pressure. And the fact that they're both, are called dark, it's just like, black ink and film noir. I mean, they have nothing to do with each other. They're just completely different. So they're just different. It's just the name is confusing, and it is confusing, but they really are different things. Question over here?
If there's two plates of dark matter and normal matter, and the dark matter is supposed to have a stronger gravitational pull, and if we're technically bobbing, how come we go up and down and up and down? Wouldn't that mean there's technically moments of weaker gravitational pull?
So the reason you go up and down, it's like any harmonic oscillator. It's like, stuff gets faster as it goes through, but then it slows down because the force is pulling it back. So it goes up, then there's gravity in the disk, it pulls it towards it, so it rushes through, then it gets down, then the gravity starts pulling, so the gravity from the disk is pulling it back up. So it's just, unless there's enough friction or something to slow it down, it's just going to keep going up and down, and that's why it does that. It's just like something bobbing on a spring. Because you were very concerned with making sure the room works and you weren't listening.
Why is it that there are certain kinds of intellects that can grasp this so easily and others that don't?
I mean, I love that. The answer to this question. It's because there's just people who are smarter than you are. Part of the reason I write this book is because look, if you're not familiar with it, it takes a while. Just like people ask me something like, "Why are you bothering to write? Like, you're never really going to understand without the mathematics." And I'm like, I don't know a whole lot about classical music, but if I read a book about classical music, I know it a little bit better. And if I read the book more slowly, and if I read more, then I'll learn more. If I talk to people while I'm reading, I'll learn more. I think part of it is, you think you're just going to magically know everything. And the fact is it's a slow process. And so, that's why it takes a while to write a book, to sort of build up all these ideas. And one of the challenges is to, it's not, I like to actually treat my readers with respect. And so not assume that they want to know the real story. But that involves actually learning stuff. And so, but it doesn't mean that they have to know it already, but it means you have to sort of build up to the point. So if you are curious about it, you will learn it. But you have to be interested enough to want to know. And if you don't care, then you're not going to learn. Thank you. Thank you. Thank you. Thank you. Thanks a lot.
I just want to thank Lisa. Let's give her another big, big round of applause. Yeah, we are. We have Lisa's new book and some of her older books as well at both of the registers, and Lisa will be signing on the other side of the store. There'll be a table there, so just form a line, and we'll get through the book signing. But thank you all for coming tonight. Thank you to the Frost. Thank you to Isa and Marvin, who are here somewhere. And I want to thank you all again. Thank you.
Thank you, Mitch.